All right, welcome back. Remember that we're talking about functions, and we talked about what it means for a function to be injective, which means that it never collapses two elements to the same element under the function. What it means for it to be surjective, which means that it hits everything in the codomain, and what it means for it to be bijective, which is just both injective and surjective. And last time we looked at a bunch of examples of functions, and the last example I left you with was the following function from R2 to R2, given by h of an ordered pair equals x plus y, x minus y. And I asked you to think about whether or not this is injective or surjective. But since the domain and codomain here are infinite sets, we can't just enumerate every element. We need to think about exactly what is happening here. Okay, so the answer is that H is a bijection. And now this is like a nice time for you to see your first proof that a function is injective and it's surjective. Okay, so remember, to say that something is bijective means that it's both injective and surjective. So generally what you do, I mean, there's many ways to prove that something is a bijection, as you'll learn in your future math classes. But generally, a nice thing to do is just prove separately that it's injective and surjective. So we prove injectivity and surjectivity separately. Okay, so now I'll let my reader know that here I'll do the proof of injectivity. Okay, so what do we need to show? We need to show that H satisfies the definition of being injective. One of the definitions we talked about was we need to show that if H of A equals H of B, then A equals B. This is one of the ways to phrase injectivity, because it says if you ever get mapped to the same thing, you must have been the same thing to start with. Now, the point is that the domain here is R2. That's a Cartesian product. So rather than thinking about elements as being A and B, I should think of them as ordered pairs. Right? So really, I'll suppose that H of x1, y1 equals H of x2, y2 for some x1, y1 and x2, y2 inside the domain of this function. So let's suppose we have 2 points in the domain that map over to the same point in the codomain. What does this mean? Well, what does H do to x1, y1? It sends it to x1 plus y1, comma x1 minus y1. That's what it does to the first thing. What does x do to the second thing? It sends it to x2 plus y2, x2 minus y2. This is what it means to say that H of x1, y1 equals H of x2, y2. Now, what does it mean to say that two elements of the Cartesian product are equal? These two ordered pairs are equal if the first coordinate equals the first coordinate and the second coordinate equals the second coordinate. Right? Then x1 plus y1 equals x2 plus y2, and x1 minus y1 equals x2 minus y2. Those are all real numbers, right? What am I trying to show? I'm trying to show that these 2 points are the same. So it's enough to show that x1 equals x2 and y1 equals y2. But now what I can do is I can add these 2 equations together. So adding these 2 equations together yields what? On the left-hand side, you got 2x1. On the right-hand side, you get 2x2. So x1 equals x2 because you can multiply by 1/2. So when subtracting the 2 equations yields, if I subtract the first one, if I subtract this from this, I get 2y1 equals 2y2. So this means that y1 equals y2. And since x1 equals x2 and y1 equals y2, therefore x1, y1 equals x2, y2, which is exactly what we needed to show. We supposed that h of x1, y1 equals h of x2, y2, and we showed that that forces these 2 points to be the same. Hence, h is injective. Okay, so here's a nice first example of how to prove that a function is injective. You use the definition. Suppose you have points that get mapped over to the same thing, write down what that means, and try to deduce that you must have started with the same points at the beginning. And of course, this is only half of the proof of this result. I now need to prove that it's surjective. Okay, let me just remind myself that h of xy equals x plus y, x minus y. So what does it mean to be surjective? We need to show for every b in the codomain that there exists an a in the domain such that h of a equals b, right? We need to show that everything in the codomain actually gets hit by something. But again, the codomain is R2. It's a Cartesian product. So I should take an arbitrary element of the codomain. So what does an arbitrary element look like? Maybe it looks like, what are some nice letters to use here that I haven't used yet? Let's let C comma D be just some element of R2. R2. Thought of as the codomain. What do I need? We need to find some xy in the domain such that h of xy equals C comma D. If I can do this for this arbitrary C comma D, that means that I can hit everything in the codomain. So how do we find it, right? So this is now just Scratch, right? So this is Scratch work. If I want h of xy to equal C comma D, well, h of xy is x plus y, x minus y. So I need x plus y to equal C, and I need x minus y to equal D. This is what I need. Well, how can I do that? If I manipulate this thing and solve, right, I get 2x equals C plus D by adding them, and I get 2y equals C minus D by subtracting them. So if I take x to be the average C plus D over 2, and y to be C minus D over 2, it seems like it'll do the trick. Take xy to equal C plus D over 2, C minus D over 2. That's my Scratch work. Now I know if I want to hit this element, I can just plug in this element. And since this element is arbitrary, if you tell me any ordered pair that you want to hit, if you want to hit the ordered pair pi comma e, I can tell you, oh, well, just plug into your function pi plus e over 2, pi minus e over 2, and you will see that you'll get pi comma e. Right, so this is all Scratch work. We sort of figured out what you need to do. Now we need to write it in a proof. So let C comma D be an R2. Now let x comma y equal C plus D over 2, C minus D over 2. Then h of xy, let's just start a new line here. H of xy is equal to h of C plus D over 2, C minus D over 2, which is equal to these two things added together, comma, these two things subtracted from each other, which is equal to C comma D. Right? And now, since C comma D was an arbitrary element, this shows that H is surjective. Because no matter which element you gave me in R2, I told you exactly how to get it as an output. So it was important here that I chose an arbitrary element of the codomain, but yeah. So that shows that this function is both injective and surjective, and therefore it's bijective. Okay, so I think this is a good demonstration of how to prove a function is injective and surjective. Another way to think about this, just FYI, you can think of this, I mean, this is a linear function. This is a linear map from R2 to R2, which means that actually all the stuff you learned in Math 308 also could have told you this. So in Math 308, you learned that you can represent this as a matrix, something like this, right? If you take a vector x comma y and you multiply it by this, you do in fact get what H does. So what you could do is you could row reduce this matrix and see that there's a pivot in every row and every column, and therefore it is injective and surjective. That's by Math 308, which is good if you're dealing with linear maps because then you can represent them with matrices. But this general abstract technique works for any kind of function. It doesn't need to be a linear function. It just, I happened to pick a linear one here too. That's because I stole these notes from when I taught 308, right? Okay. One word of warning, though, is that there are many crazy functions in the world. Really crazy functions. Okay, so everybody is used to thinking about fx equals x squared, maybe even h of xy equals x plus y, x minus y. But I don't want you to get the thought that every function is given by some nice operations applied to some inputs. I mean, these are like super, super nice functions. They're continuous in the appropriate sense of continuous, because this is from R2 to R2, but there's a way to define continuous there too. I mean, f is like infinitely differentiable. I mean, you can only take 3 derivatives, but then, I mean, you can continue taking derivatives. But there are really crazy functions in the world. As you advance through your math coursework, you'll learn functions that have all kinds of pathological properties. Right, okay, so mathematicians use the word pathological for when something really doesn't, some mathematical object is really not well behaved. A nice book, there's a cool book called Counterexamples in Analysis. Which shows how all kinds of crazy stuff can happen with the real numbers, with functions, with series, with sequences. So I just like leafed through it before I record this lecture. And there's a continuous function. There's a continuous function from R to R such that f is continuous, but nowhere monotonic. So monotonic means like that you are either weakly increasing, right? So either weakly increasing, right, maybe even flat, or weakly decreasing on some little interval, right? So on you draw some crazy function, but like on this interval here, between here and here, the function is monotonic. It's monotonically increasing. It seems like if you draw a function just that's continuous, that's, you know, you don't lift your pencil off the paper, it seems like you should always be able to find some small little area where it's either weakly increasing or weakly decreasing, right? So a flat function also counts. That's not flat at all. A flat function counts. You would say it's monotonic here. It's monotonic everywhere because it's weakly increasing and weakly decreasing. But it turns out that there's a function that is continuous, but there's no little interval where it goes up, where it's monotonic. It's hard to believe this fact, but this book gives a nice construction of a continuous nowhere monotonic function. There's also a function that's continuous everywhere, but nowhere differentiable. So these functions are somehow extremely crazy and yet still continuous. Right? You can't even imagine what they look like. So this is a cool book. It's a nice book. It's a nice thin book to have on your bookshelf, just to remind yourself that the real numbers are crazy. So like when you're trying to analyze a function, you might not have like a really nice clean formula for what it does, or that formula might like not be very easy to understand, right? So let me give you an example of a more interesting function that we can think about, at least a little bit more interesting. So suppose that f from a to b is just any function. Any function you want. You could take x squared if you want from r to r. But let's now define a function g that goes from b to the power set of a. How am I going to define this? Defined by what g does to an element y in b is it spits out the pre-image of the set containing y. Okay, and then I can ask, is g injective? Is it surjective? Okay, so this is like, I would say, a genuinely interesting function in that, I mean, even to understand the definition, we need to think hard about this. This function h, which we proved was bijective at the beginning of the lecture, is in some ways not a very interesting function because it's very easy to understand. You sort of know exactly what it does. There's no mystery to it. And then learning to prove it's injective or surjective is sort of just a mechanical rote operation. But this function g is kind of interesting. It's hard to understand what it's doing. So in particular, we should look at some small examples. Okay, so just to remind you, so this f is any function, g is a function from b to the power set of a, and I've defined g of y to be the pre-image of the set y under f. So let's just take a very small function. Let's let a and b just be 3-point sets, x, y, z, a, b, c, and let's send x to a, let's send y to c, and let's send z to b. Let's suppose that this is our function f. So what is g? So g is the function from b to the power set of a. That means you need to be able to plug in every single element of b into your function g. So what does it give you? So g of b here is defined to be the pre-image of the set b. That's by the definition of the function g. And what is the pre-image? The pre-image is all of the elements in a that map over to b. Man, I probably should have chosen better letters here. You know what? Let's call them A1, A2, A3, and B1, B2, B3, just so we can have a good handle on which thing is in which set. Okay, A1, A2, A3, B1, B2, B3. This will be less confusing, I think. Okay, so G goes from B to the power set of A. And G of B1 is the pre-image of the set containing B1. So that's the set of all elements that map over to B1, but that's just the set containing A1. Right? Again, this is defined to be the set of all elements that map over to B1, but that set only contains a single element, which is A1. And notice that this is, in fact, an element of the power set of A. That's the codomain of my function, so it better be spitting out things in the power set of A. And it is clear that if you take the pre-image of an element of B, you'll always get some subset of A. In this case, it's a one-element subset. Okay, so G of B2 here is just all the things that map over to B2, which in this case is just a set containing A3. G of B3 is the pre-image of B3, which is just the set containing A2. So this does, in fact, define a function from B to the power set of A. Well, just for this small example, is G injective and is it surjective? Well, in this example, it's definitely injective, right? But I'm not talking about f, I'm talking about this function g. It's definitely injective because these three different inputs, they all mapped to distinct outputs. So this g is injective. Okay, of course, f is bijective, but that's not what I'm asking. I'm asking about g. So we've now understood what G is for this specific F, but this is just a specific example. So the answer to this question is G injective. As far as we know it, at least sometimes, because we came up with an example where it's injective. We could ask, is it always injective? Is that a thing that we can maybe prove? What about surjectivity? Surjectivity, it's actually clear that this function is not surjective. Why? Because the codomain of G is the power set of A, and the power set of A contains 2 cubed elements, right? It contains every subset of A. And here this function only spits out 1 element subsets of A. So it only hits 3 things in the codomain. So the image of G has size 3. The codomain has size 8. So it's not surjective. But again, that's only for this specific G. In general, is it surjective? What we figured out is not always, because we found an example where it's not surjective. So it's not always surjective, but we could ask, is it ever surjective? These hopefully should be natural questions for a math major to ask. You could ask a more finer grained question too, right? You could ask, under what conditions, or under what hypotheses is G injective or surjective? Right? Maybe, I mean, it should be related to some properties of F, right? Depending on what F is, maybe you can say if F has this property, then G is injective, or if F has this property, then G is surjective. Maybe if and only if. So now that we've understood this specific example, I think we're still not quite ready to understand the general example because we've only looked at a single function, F, and that function was bijective, so it was kind of special, right? So we should think about what happens if we change F, what happens to G. Okay, so let's try a different F. So let's consider an example that isn't bijective. So let's again take A1, A2, A3. Let's call this function G. No, let's not call it G. Let's just call it F again, because I've reserved G for the other one. So let's call this function the same thing, F. And in this case, let's send, let's make it both not injective and not surjective. Let's send 2 things to B3. Let's try this. So if this is our function F, this is A, this is B, let's think about G. So G goes from B to the power set of A. So what is G of B1? Well, that's still just the preimage of the set containing B1. It's all the elements that map over to B1. So it's just A1, the set containing A1. What is G of B2? Well, G of B2 is F inverse of the set containing B2. So, sorry, not F inverse. It's the preimage of the set containing B2. So it's all the elements of A that map over to B2. But there are no elements of A that map over to B2. Right? So this is just the empty set. What about G of B3? G of B3 is all the elements that map over to B3. So it's a 2-element subset. It's A2, comma A3. So in this example, is G injective and is G surjective? Well, G is still injective because it spit out 3 different subsets of A, 3 different elements of the power set. So these are all different. So G is injective. Also, G is still not surjective because the power set of A contains 8 points, but it only spit out 8 elements of the power set. Okay. So these two examples, now maybe we're on our way to kind of understanding something. If we think about what's happening in these two examples, let me just make some observations, which maybe you could make if already, or maybe if you did some more examples. Okay, so one thing to notice is that if you look at the sets that G spits out, in other words, if you look at the image of G, every element of A needs to appear exactly once, right? Because every element of A maps over to something inside of B. And so if I look at this function G takes the preimages, it takes all the elements that map over to a specific element of B. If I look at every single element of B, every element of, A1 has to go to one of them and only one of them. A2 has to go to one of them and only one of them. A3 has to go to one of them and only one of them. So I'll have to put A1, A2, and A3 in exactly one of these preimages. So a thing to notice is that every element of A appears in exactly one set in the image of G. Another way to say this, okay, which means two things. Which means that if you take the union of all of these sets, you have to get all of A, because every element in A appears exactly once. So when you take their union, you get everything. And also these sets have to be disjoint from one another. They have to intersect trivially because an element in A can only map over to a single thing in B. So the image of G consists of disjoint sets whose union is A. So altogether, what this means is that the image of G is a partition of A. A partition just means that you took A and you broke it up into a bunch of subsets. Okay, another thing that we learned from this is that it seems really hard to make G surjective because the power set of A has 8 elements, and you're only ever going to get 3 elements in the image of G. Right, so I think I might be tempted to say that G is never surjective, because the power set of A contains 2 to the size of A elements, but the image of G contains the size of B elements. But it is possible for these two things to match up. If A is small and B is pretty big, I guess we could hope for something to happen where G is surjective. But actually, this insight about the partition tells us even more. So what we need is we need the partition to consist of every element. I'm really writing impossible to read here. Of the power set of A. If you think about it though, right? Like, so if you took A to be a 2-element set, then its power set is going to be the empty set A, B, A, B. So like you could never take everything in the power set and get a partition, because A appears in 2 sets here, which could never happen in the image of G. but it actually is possible, but it's only possible if A is a set of size 1. Sorry. What I should have said is the image of G contains exactly A elements, size of A elements. So, right, most of the time, this thing is just way too big for G to be surjective. But it turns out that it is actually possible. So it's possible to have G surjective if the size of A equals 1. So what's my example? So just take a single element in A and map it over to B. Let's say B1, and then just leave B2 alone. Then if you look at what G does to here, G sends B1 to the set containing A, and it sends B2 to the empty set. And this is the entire power set of A. But this is the only time that the power set consists of a partition of A. So you could say that G is surjective if and only if the size of A equals 1 and the size of B is bigger than 1. It turns out that this is an if and only if. Okay. What else did we learn in terms of injectivity? Well, again, the things in the image of G form a partition of A, right? Each element of A appears once and only once in one of these sets, which means that it seems like G is basically always going to be injective, right? Because these sets sort of have to be different because A1 can only appear in one of them. So whichever one A1 appears in is different from all the rest of them. The set that A2 appears in is different from all the rest of them because it contains A2, but the rest of the sets don't contain A2. So the fact that they're disjoint sort of means that all the sets are different, but it doesn't, because there is a case when you could take two of the same set to be disjoint, which is if you take the empty set. So let me write that down. G seems very likely to be injective since sets in the image of G are disjoint, which sort of seems like it means that they're different, but it doesn't. So let me give you an example. It's a very simple example. Just send A over to B1 and don't hit B2 and B3. Then G of B2 is the empty set is G of B3, but B2 is not equal to B3. But those are the only two, that's the only way to get disjoint sets that are the same. So G is injective. Uh-oh. OneNote really doesn't seem to like me this week. G is injective if and only if the image of F hits every element except maybe one. Equals the codomain of F except maybe -1. You're only allowed to miss one element, because if you miss more than one element, you'll get the empty set twice in the image of G. Otherwise, the sets will all be different because they'll contain different elements. Okay, so I just wanted to give you an example of a function that was, or a family of functions that were kind of interesting, because I don't want you to get this mistaken idea that every function is a super nice, easy to understand function. Sometimes you have to do some work. Okay, so hopefully that was worth the amount of lecture time that it took, which was not insignificant. Okay, So let me now move on to the following question. Here's your question. Suppose A is a subset of B, but it's a strict subset. Can you find a bijection F from A to B? Okay, so let me talk about what this question is saying. So A is a subset of B that's not equal. This means that somehow A is smaller than B. Right? A is strictly contained in B. There's some elements of B that are not elements of A. So the picture of this is that A sits entirely inside of B, and there's even some elements that are not in A but are in B. So this says that A is smaller than B. We haven't defined smaller, but A is smaller than B. Okay, on the other hand, a bijection sort of matches up elements between the two sets that you wrote a bijection between. So to say that you have a bijection between two sets kind of is saying that A and B have the same size. That's if I'm reading this, like if I'm trying to understand the intuition behind this, I would read this first condition as saying that A is smaller than B, and this condition as saying that A and B are the same size. So actually, one problem with this intuition is that this intuition that I'm having is only for finite sets. If I draw a picture like this, so there's 4 elements in B and 2 of them are in A, it's clear that there's no way that I could draw a bijection from A to B because I could just never be surjective. There just is no way. So if A and B are finite, the answer is definitely no. Basically for this reason, right? If they're finite and A is a strict subset of B, it means that B contains more elements, but the image of F contain only as many elements as are in A. So there's got to be something in B that doesn't get hit by F. However, if A and B are infinite, it turns out that it's possible. Basically because infinity is kind of crazy. So let me give you some examples. Let me just start a new page. One, let's let A be the positive reals and B be the real numbers. Then F of X, F is from R to R greater than 0 to R, defined by F of X equals natural log of X, is a bijection. Right? The graph of this function is, it looks like this. So its domain, it hits everything in the domain. We actually already discussed that it's an injective function and it's surjective when you consider it as a function from R greater than 0 to R. And this set is a strict subset of this set, right? So even though this seems like a smaller set than this set, you can still find a bijection between them by taking the natural log. Okay, 2, I could do even better because this seems like, okay, well, this is A is sort of smaller than B, but it's not that much smaller. It's like half as big. I can do you a little better. Take negative pi over 2 to pi over 2 for your domain and take all real numbers as your range. And let's define a function f from a to b by f of x equals the tangent of x. Right? This function from negative pi over 2 to pi over 2 looks like this. Right? It's increasing, therefore it's injective. And then it goes off to infinity and to minus infinity and hits every number in between, so therefore it's surjective. And so this gives a bijection between this really rather small interval and this, which is all the real numbers. So those two functions, sorry, those two sets you can put in bijection, even though this is really a strict subset of this, really, really small subset. Okay, let me ask you to come up with one now. Let's suppose that I take a to be the natural numbers minus 0. So here I'm including 0 in the natural numbers, but then I'm taking them out in a, and b to be the natural numbers, right? So that a is 1, 2, 3, 4, etc. B is 0, 1, 2, 3, etc. So a is a strict subset of b. Is it possible to find a bijection here? Okay, so the answer is yes. One thing you can do is you can just send x to x minus 1. So that's a nice easy bijection. That's injective because if two numbers are different, then if you subtract 1 from both of them, the resulting numbers are still different. It's surjective because you can get every number in B by subtracting one from some number in A, and particularly just add one thing. To get B, you just add B plus, you just take B plus 1 and put it into your function. But this is not the only answer. I could take, for example, f of 1 equals 1, f of 2 equals 0, and then I could take f of x equals x minus 1 for all x greater than or equal to 2, greater than or equal to 3, say. Sorry. Right, so I could just mess up some stuff at the beginning, and then I could just take x minus 1 all the rest of the way. Or I could do all kinds of crazy stuff, right? So there's many possible bijections here. Okay, let's think of some more. Let's call this example. I realize I've skipped an example in my notes. I'll just leave it in the notes. You can read it in the notes. Or let's let A be the natural numbers and B be the integers. Again, it's very clear that there's a strict containment here, right? There are way more integers than natural numbers. It seems like there's about twice as many. That's what it kind of seems like, but we can find a bijection, f from A to B. So actually what I'll do is I'll ask you to do this between now and the next lecture. So at the start of the next lecture, what I'll do is I'll write down some possible bijections here. So answer next lecture. You should actually try to come up with a bijection, but before then. And then my last thing is let A be the natural numbers and B be the real numbers. Find a bijection, f from A to B. Okay, so the point of this last example is just that if you take infinite sets, even if it seems like A is smaller than B, which it does in all of these cases, it might be possible to write down a bijection between them, which somehow says that they're the same size. So I want you to try to come up with a bijection between the naturals and the integers. Is that possible? Is it not? Between the naturals and the reals? I still have a few minutes, so let me include that last example that I skipped earlier. If I let A be the closed interval between 0 and 1, and B be the closed interval between 0 and 2, that's a strict subset. It again seems like B, there's twice as many elements in B, but there's a nice easy bijection between these two. you just take f of x to equal 2x. So even though, you know, a is this interval, a is this interval, and b is this interval, those two intervals, there's a bijection between them. In other words, they sort of have the same number of elements somehow. Okay, so next lecture, I'll begin by discussing the answers to 4 and 5. But you should really try it on your own. Okay, see you then.